Hi, welcome to this section of the differential equations tutor. And in this section, we're going to continue working where we stopped in the last section. We did a great introduction of what is a differential equation. We worked one equation all the way through. We got the general solution, we got the specific solution, we talked about initial conditions. You guys are well on your way to really mastering this material. Now, what we're going to do now, we're not going to learn anything new. We're going to work some problems related to what we learned in the last section just to sharpen your skills a little bit. So here we go. Start with something a little bit easier. What is the order of the following differential equation? T to the fourth power times the third derivative of x with respect to time plus t times dx dt minus x is equal to t to the seventh power. Now, by the way, before we even begin, you see, this is a differential equation that is where you start getting into problem solving these things. You know, and the last time we could just simply get the derivative by itself and then integrate a bunch of times. Well, here you got a bunch of problems. You've got t's out in front here. You've got two derivatives instead of just one. So this equation involves the third derivative of some quantity plus the first derivative here. And there's just it's a general, just a nasty thing. So we're going to devote a lot of time in this course to getting our skills up where we can do these kinds of problems. But for now, forget about that. What is the order? The order is just simply, what is the highest derivative you have? In this case, we have a first derivative here, we have a third derivative here. So the order is 3. That's a third order differential equation. All right, there's another one here. What if we have x to the 8th plus, times dx dt plus the seventh derivative of x with respect to time is equal to x plus t to the ninth power. So what is the order of that differential equation? So we have a first derivative here. There's no derivative over here at all. This is the seventh derivative. So this is the seventh order. Okay, I really think that's enough of these kinds of problems. I just wanted you to see some more complicated differential equations to realize that, you know, a lot of times these equations are not going to look as simple as what we talked about there in just the last section. This pretty complicated little differential equation. So the next kind of problem that I want to do is I want to verify that x of t is a specific solution, that's solution, to the ODE, ordinary differential equation. So, you know, just like in algebra, I mean, let's just say here, what if you have the equation, x minus 2, is equal to 4. X minus 2 is equal to 4. You all know how to solve that, right? You know that x is equal to 6 because you can take the 2 and add it to both sides and x is equal to 6. And you could probably do that in your head. And you know that it's equal to 6. Why? Because if you take this answer that you got and you take it and you plug it right back into the equation, it should equate, right? So if you put it in there, you'll get 6 minus 2 is equal to 4. Is it equal to 4? And so you say, yes, 4 is equal to 4. So that is a solution to the equation. And you spend a lot of time doing that in Algebra 1, right? Because the concept of having an equation and having a solution was foreign to you, but you knew that if you take the solution, you put it back into your problem, you're going to be able to verify that you have the right answer. These differential equation things, they're not any more magical. There is an equation and there is a solution. It's just that all of your solutions are going to be a function. And so in order to verify if that solution is really an answer, is really a solution, a valid solution, you need to take it and plug it back into your differential equation. So that's what we're going to do. So let's say in this problem, let's say I have x is equal to e raised to the 3t power. That's my solution. And the differential equation that I want to see if it's a solution for is third derivative of x with respect to time minus 9 times the second derivative of x with respect to time, and that's equal to 0. So again, you can see this is a much more complicated differential equation. It's a third order differential equation because the highest derivative is 3. I have a third derivative here and I have a second derivative here, and I claim that this guy is a solution to that differential equation, or I'm asked to find out, is that true? So the way we need to do that is we need to plug it in there. But you have these derivatives, so what do? Well, you need to start taking derivatives here before you can really do anything. So let's start taking derivatives of this guy. So we'll say dx with respect to time is equal to, now this is a nice exponential. Exponentials are very nice because the derivative is very easy to calculate. The derivative of this is just simply equal to e to the 3t, which is the exponential itself, times the derivative of the exponent, which is 3. So you're going to end up with 3e to the 3t. That's the first derivative. Now the second derivative, d squared x dt squared, the second derivative is taking this and taking the derivative of again. So you're going to have the same exact thing. You're going to have 3e to the 3t, that's what you have here, and then you're going to multiply that by the derivative of the exponent again. And so when you have 3 times 3, you're going to have 9e to the 3t. 9e to the 3t. That's the second derivative. And we need to go up to the third derivative because our equation has 3 derivatives in it, so we'll take one more derivative. The cubed, I shouldn't say cubed, third derivative with respect to time is equal to, and we'll take the derivative of this again. So we have 9e to the 3t, same as before, but we're multiplying by the derivative of the exponent, which is just 3. And so we'll get 27e to the 3t. And now we have everything we need to verify if this is really a solution to this or not. Because really, we don't even need the first derivative. The only reason we calculated that was to get the second and the third derivative. So now that we have it, let's put it in there. Third derivative with respect to time is this. So we have 27e to the 3t minus 9 from our equation times the second derivative, which is given by this, which is 9e to the 3t. And the question is that equal to 0? Because when I put them in there, whatever I get, I should get an answer of 0 if that is really a solution. So here I'm going to have 27e to the 3t, and here I'm going to have 9 times 9 is 81, e to the 3t, and that is not equal to 0. There's no way this is going to be equal to 0, so this is not a solution. So this guy here is not a solution. That's the answer to the problem. No solution. This is not a solution. So that's what you're asked to do a lot of times. You'll be given a differential equation. You'll be given a function that you're asked to say, hey, show me if this is a solution or not. And so you're going to have to plug it in. But in these kinds of problems, instead of algebra, instead of just putting it in there, you'll have to take derivatives first according to what kinds of derivatives are in the problem. But once you get to that point, it's very easy because you're just taking them and you're putting these derivatives into the problem where they go, and you're just seeing if it satisfies the equation or if it doesn't. All right, let's do another one of those. And let's say that your solution, proposed solution, is x is equal to natural log of minus t, and that would be defined for t is less than 0. The reason it has to be defined for t less than 0 is because this natural log function is not defined for negative argument, so you're going to have to bound t to be less than 0 so the argument will be positive. It's sort of a technicality. I just want to put it in there in case some of you guys are wondering how I can do that. So that's a proposed solution, valid only for t less than 0. Now, the differential equation I have is t times the first derivative of x is equal to 1. Now, I usually do not write differential equations with these primes in there. I mean, a lot of books do. I usually don't. But you'll see it different ways, and so I'm just going to get you exposed to that. So this is a first derivative of x with respect to time. So what we need to do is take this solution, plug it in here. In order to do that, we need to take the first derivative because our problem involves the first derivative. So let's do that. So x prime, which is the first derivative, is equal to, the derivative of a natural log is just simply 1 over the argument. But we have to multiply by the derivative of the argument. This is a chain rule, right? So the derivative of this is going to be -1. And so x prime, the derivative of x, is going to be 1 over t. That's what we're going to get. Now, if we take this and we plug it into our differential equation, what we're going to get, switch colors, we'll get t, which is in the problem, times the derivative, which is 1 over t, and that question mark is equal to 1. And you'll see here you'll have t over t, so you will have 1 is equal to 1. So that is a solution. So this is, I'll put yes, is a solution. And that's what you would write in your test. So it works exactly the same as Algebra 1. You take it and you plug it in. It's just that you'll need to take derivatives along the way. So, I could work a few more of these kinds of problems, but basically this is an exercise in basic calculus. I mean, if you know how to take derivatives, then you'll be able to do that. And if you know how to plug in something into an equation, which I know all of you can, then you'll basically be able to find out if a solution is valid or not. Now, most of the time in differential equations, that's not what you're doing. This is sort of an introductory section, so we're getting our feet wet showing you what these things are all about. But really what's going to normally happen is you'll be given a differential equation that you have no idea what the solution is, and you'll have to calculate the solution. So that's the kind of problem that we're going to work on next. And they'll be simple. They will be simple because this is a simple section or an introductory section. I say they'll be simple. I mean, they'll have steps to them, but they're not going to be like you'll see in the next few sections where the process is a lot more involved. So let's find the solution, the general and the specific solution to the following differential equation. Second order derivative or second derivative with respect to time of the function or is equal to 3t plus 1. So this is your differential equation, and your initial conditions are going to be given in your problem. At time is equal to 0, the position is equal to 2. And at time is equal to 0, the velocity is equal to 3. This is the position, and this is the velocity because this is the derivative of x. So this is the velocity at a position at a time of t is equal to 0 is equal to 3 meters per second, or whatever it is you're talking about. The position is given by this other guy. The initial conditions are used later, after you get the general solution. So what we need to do is look at our problem, and this will be the thing that we do every time. We look at it, and we go through a little mental checklist. What can we do? The first thing that you should always look at when you're looking at a differential equation is, can I simply integrate it? Can it be so simple just to integrate it? Because the other techniques are much more complicated, not so straightforward, and that's why the course has a bad reputation. And we'll get to those. It's not going to be that bad, I promise you. But for this one, you can look and say, yeah, I've got a derivative all by itself over here, and I've got a nice function of time. So I can integrate both sides with as a function of time and get the answer. So let's do that. So what I'm going to have is the integral of the second derivative of x with respect to time. I'm going to integrate with respect to time because that's what the derivative is with respect to, and I'm going to carry that integral over to 3t plus 1 dt. And so what I'm going to end up with on the left-hand side is I'm going to take the second derivative, and it's going to turn into a first derivative because I've taken one integral. So I'm done on the left-hand side. And on the right-hand side, I'm going to take this simple integral. So it's going to be 3/2 t squared plus an integral of 1 is just going to be t. And since I'm doing an indefinite integral, I'm going to have a constant of integration. I'm going to label it c sub 1 because I know from previous experience that I'm going to integrate it again in a second. I'm going to have a c sub 2. Now let me give you one piece of advice that maybe you've already taken from your calculus or figured out, or maybe you haven't. You need to get good at this. Trust me, it'll save you a lot of time. Get in the habit of writing your pluses like this, up and down like this, and get in the habit of writing your t for time with a little thing at the bottom, like this. Get in the habit of it. Write it a million times, because I guarantee you, if you put t squared plus plus plus, it's going to look like a mess. You're not going to know what it is. You have to get in the habit of putting that in. Just while I'm thinking of it, a lot of people, I didn't do this till halfway through college, but this is the letter Z. If I were you, I would get used to writing the letter Z with a little thing across it. I used to think people were weird for doing that. But when you're writing down an integral 2z squared, if you write it really quickly, 2z squared, I mean, what is this? 2, 2, 2? Or is it z, z, z? Or is it z, whatever, whatever? You need to write your z's with a thing like that. That is going to save you a lot of time, and it's going to save you a lot of frustration, because if you look back through your work, you will eventually make a mistake, and you eventually will not know what the heck you were doing. So even this is kind of hard to read, but I know that this is the variable. So I'm going to leave it like that. So we got 3/2 t squared plus t plus constant 1. So that's a good first start. Now let's take this and let's integrate it again, because we need to isolate the variable. So Let's integrate dt. Whoops, it's going to be dx with respect to time. And we're integrating with respect to time. And on the right-hand side, we're going to integrate 3/2 t squared plus t plus c1. And it's an integral over dt exactly as it is on the left-hand side. So we're just integrating again, just like we did for f is equal to ma. On the left-hand side, we're just going to get back our function that we're actually trying to calculate, x. We know it's a function of time. And on the right-hand side, you need to do this simple integral. It's a nice polynomial integral. 3/2 over 3t cubed, so it's 1 plus the exponent, plus 1/2 t squared, so you have a 1 out front, so 1/2 t squared, 1 plus the exponent, plus, for this constant, it's just going to be c1 times t, because that's just a constant there, plus, and you have a constant of integration, so we'll call it c sub 2 this time, because it's a totally different constant of integration than the other guy. Now what we're going to do is rewrite this. So let's rewrite it. Really, you know, when you think about it, this is 3 over 1. So really, this 3 kind of cancels with that 3. If you want to think about it, you can flip this fraction over and multiply, and you'll see that this 3 will be on the bottom. It'll cancel. So what you're really going to have for the final answer here for the general solution is going to be 1/2 t cubed plus 1/2 t squared plus c1 times t plus c2. So you have 1/2 t cubed plus 1/2 t squared plus c1 times time plus c2. So you see where all the t's come in handy, right up a little thingy at the end of it. It's going to help you out a lot. That's the answer. This is the general solution. So I'm going to circle this. I'm going to write down general solution. That is the general solution. You just integrate as many times as you need, and notice that there's 2 constants of integration here. And that means that this is an infinite solution set, basically. There's an infinite number of ways in which this solution could be constructed. They're all going to have this stuff at the beginning because the problem lends itself to that, and they're all going to have this general form. But depending on the initial conditions that are also given here, we'll use in a second, is going to define what C2 and C1 are. It's going to define what the actual specific solution is to this problem. All right, now let's go ahead and do that. Let's go ahead and do that right now. So we have the initial conditions up here. Let me rewrite them. So I'm going to put a little thing here. So what we have is at time of 0, the position is equal to 2, and at time of 0, the velocity is equal to 3. So since we already have x of t right here, let's work with the first initial condition. So x of 0 is equal to, and let's plug in 0 here. So we have 1/2 0 cubed plus 1/2 0 squared plus c1 times 0 plus c2, just plugging in 0, and that's equal to 2. Right? So what you're going to see is what you might expect. That goes away, that goes away, that goes away. And so what you're going to have here is constant 2 is just simply equal to 2. So we've solved for one of the constants. So I'm going to kind of box this because that's important for later. Now, let's move on and use the other initial condition, and I'll switch colors there. And now we need to plug in what the velocity is at time 0. Now, the velocity, you know, you could just take your answer that you have here and you could take the derivative of it and get the velocity. But since you did this problem by integration, if you just look right back up here, you'll see that you have the velocity right here. dx dt is the velocity. This is the function of it. So let's go ahead and write that down here. And what we'll have is x prime of 0 is equal to, if you look up here, 3/2 t squared. So you have 3/2 0 squared, because this is at time 0, plus t, which is 0, plus constant 1, which is from right here, and that's going to equal to whatever our initial condition said. All we did was we plugged in t is equal to 0 into the velocity equation, plugged it in there, and we set it equal to what was on the right-hand side. And so we have more cancellations there. And so what we're going to find is that, well, let me write this in a different color, is that C1 is equal to 3. Okay, so that's important. So now that we have that, we can write down the final answer for the specific solution. So x of t for the specific solution is equal to 1/2 t squared plus, whoops, that's t cubed. 1/2 t cubed from here plus 1/2 t squared from here plus constant 1, which is 3t right here, plus constant 2, which is 2. And this is the specific solution. So I'll put specific solution. Notice there's no constants of integration anywhere in there. 1/2 t cubed plus 1/2 t squared plus 3t plus 2. This is the specific solution to this problem. So this is the general form, describes infinite number of solutions for that particular differential equation. Our initial conditions drive what our constants are. That's going to lay out a specific solution. And that's the answer to the problem. So in this problem, we basically just integrated a bunch of times. And when we got to the final answer, we applied the initial conditions and went on our merry way. So we'll do a couple more like this just to kind of show you and so that you can get comfortable with it. But don't forget that this is something you should always look for, and make sure that you're not overlooking something simple. Most of the time your derivatives are not going to all be on one side that you can just do a simple integration like this. But it's a great way to start learning how to do differential equations. Let's say the next problem is the third derivative of x is equal to 6. That's what the three little marks there are. And let's say that the initial condition is x of 0 is equal to x prime of 0, which is the first derivative, is equal to the second derivative, and all of those are equal to 0. So the position at time 0 is 0, the velocity at time 0 is 0, the acceleration at time 0 is 0. That's a good way to think of it. So everything starts basically at rest, not moving at all. That's what that really means. So if I'm going to work with this, personally, you don't have to do this. I just like to rewrite it. And that's going to equal 6. And so that's what I'm going to do. And what we're going to do next is we're going to integrate it. Because we have our derivative on one side. Whoops, you see I made a mistake right here. It's d cubed x dt3, because it's a third derivative. Okay? We're going to integrate that. So let's go ahead and write the integral sign right here. So we'll say third derivative of x with respect to time integrated over dt is equal to the integral of 6 dt. So it's a super simple integral. It's just that it's a third order equation because it's a third derivative there. So you're going to have to do 3 integrals basically to get to the general solution. So let's go ahead and do them really quickly. They're not going to be hard. Integral of this guy is going to be the second derivative of x with respect to time. Because we take the one integral, and then over on the right-hand side, we're going to get 6 over, actually that's a constant, so we'll have 6t, because that's just simply a constant. So we'll have 6t, and then we have a constant of integration, so we're going to put c sub 1. So we're going to always do the constant of integration and label them. All right, so that's the first integral that we do. Now let's go ahead, try to save some board space. Let me go ahead and go this direction along the board, and let's integrate it again because we need to continue integrating. So over here we're going to have second derivative of x with respect to time. We're going to integrate it like this, and it's going to equal 6t plus constant 1 dt, and we're going to integrate the right-hand side as well. So we're just doing an integral. I'm just writing it over. I don't like to write something down and then put integrals on top because then you lose the flow of it. So we're integrating it, and then when we do this, we take this and write down what we have here. On the left-hand side, we're just going to get back the first derivative, dx dt is equal to, and on the right-hand side, we're going to integrate this, so it's going to be 6 over 2t squared plus, and here we have a constant, c1 times time, and so we're done with that, so we're going to have another constant, c2, just a basic integral of a polynomial. So we'll have 6 over 2t squared plus c1t plus c2. All right, and this is going to be equal to, just doing a little simplification, this is going to be equal to 3t squared plus c1t plus c2, and that is the first derivative. So we obviously need to integrate it again, so let's do that. We'll have the integral dx dt with respect to time is equal to the integral of this stuff, 3t squared plus c1t plus c2. And that's going to be integrated with respect to time. And so what we're going to have right here is just x of t, because we're taking the integral of this derivative. And here, it's another nice polynomial. These are not terribly hard to integrate, so it's going to be 3 over 3 t cubed, right? And then here's going to be c1 over 2 t squared, because that's a function of time there, plus c2t. And now we have to introduce yet another constant of integration. Now, there's a couple things I want to tell you here. Let's go ahead and do it one step at a time. Let me write this down in brown, let's say. Let me simplify this a little bit. X of t is equal to, this is just 1, so I'm going to make this t cubed. What do I do with this? This is c1 over 2. c1 over 2. Well, you see, 2 is a constant, and c1 is also a constant. So when you divide them, all you're doing is arriving at another constant. So you don't really have to carry it through as c1 over 2. You can just simply write it as c1 t squared. And you'll have c2t plus c3. It bears repeating. You know, you introduced this constant of integration way back when, but then as you integrate it again and again, you started dividing a constant by something else. So it's kind of silly to keep it written as c1 over 2 because that itself is just another constant. So we're going to relabel this as our final constant of integration that we care about in the final answer. And this is the general solution. We have 3 constants of integration. And notice for every problem that we've done, we have as many numbers, constants of integration, as we do initial conditions, which also is equal to the order of the differential equation. All of that stuff is you're going to see over and over again. Whatever the order of the differential equation you have, that's as many constants as you're going to have in your general solution, and that is also going to be as many initial conditions that you need in order to do and solve for the specific solution anyway. So t cubed plus c1t squared plus c2t plus c3, that's the general solution. Now we'll draw a little line and see if I can do this without crowding the board too much. So our initial conditions, it's basically easy because all of them are at time 0 and they're all equal to 0. So we'll just put in, let me change colors. We'll just put in at time 0, what we're going to have is 0 cubed plus c1 times 0 squared plus c2 times 0 plus c3, and that's going to equal 0 because all these initial conditions were equal to 0. And so when we do that, you know, that means nothing, that means nothing, that means nothing. And so at the end of the day, constant 3 is equal to 0. That's just equal to 0. All right, now in order to apply the next one, we need to find out an equation for the first derivative and evaluate that at 0 and equate it to 0. So the first derivative we have right here, dx dt. That's the first derivative, so we're going to use that right there. So the first derivative evaluated at 0 is equal to 3 times 0 squared plus c1 times 0 plus c2. And that's also equal to 0 because all these initial conditions in this particular problem are equal to 0. So that cancels, that goes out. And so what we're going to be left with is c2 equal to 0. And finally, the third initial condition involves the second derivative, so we have to go farther up our problem and realize that this is the second derivative. So let's use that. So x double prime at 0 is equal to 6t, so 6 times 0 plus c1, and that's equal to 0 at that time as well. And so this disappears, and so we know that c1, let me go ahead and change colors here, c1 is equal to 0 as well. So all of that work just to show ourselves that the first constant is 0, the second constant is 0, and the third constant is 0. And so when we do that, the specific solution to our particular problem with our particular initial conditions is x is a function of time, t cubed from right here, plus, well, we have c1 times this, that's 0, c2 is 0, c3 is 0, so really there's nothing else there. So that is the specific solution. So this followed exactly the same method. We had a differential equation, third order, third derivative over here. We took an integral and we got this. We took the integral of this and we got this. We took the integral again and we finally got the general solution. We just had to keep our constant straight, and when we divided this constant by something else, we relabeled that our new constant, C1, because it's in the same location. This became the general solution, and in order to calculate the specific solution, we had to plug in the initial conditions into the different derivatives, calculate what the different constants were, and then put those right back into there. So it's a very repeatable process. You know, you're going to apply this all over the place. You're going to get a specific, a general solution. You're going to get a specific solution by looking at your specific initial conditions. So what we're going to do now is erase the board, work one more problem. It's going to be a little more involved in terms of how we're going to do it, but it's the same overall idea. Okay, so our last problem in this section is going to be a second order derivative of x with respect to time. And it's going to look awfully simple. Te to the t. T times e raised to the power of t. And the initial conditions, x of 0 is equal to x prime of 0 is equal to 0. And by the way, these initial conditions, they're not always going to be equal to 0 like this. This could be equal to 5 or whatever the initial condition is. It's just in this section, since you know it makes more sense to explain the details without getting too bogged down in really complicated math. We're trying to keep it a little bit simple, but just keep in mind that you can have initial conditions that are not always equal to 0 like this. You'll just have to plug in the appropriate number. So first thing you do when you look at a differential equation, you look at it and you say, well, I have this derivative over here and I have this function of time over here, so I could just simply integrate that guy, which is how we've done all these problems. So let's try it. What we're going to have is we're going to integrate this guy. And so when we integrate the left-hand side, what we're going to end up with is the first derivative with respect to time. Once we do this integral, we're going to end up with this. So if I put a little integral sign there, that's what we would end up with. And on the right-hand side, we still need to do the integration t. As the problems get longer and longer, I'm going to do my best not to shortcut too much stuff, but I'm going to have to shortcut some of the writing, because literally if I wrote every single thing down, I mean everything, like I was doing a minute ago, then the problems would get just so long and it would be harder to follow. So in this case, instead of rewriting this and writing an integral sign and then doing the integration, I'm just telling you, here, look, I'm integrating both sides. The integral of this is equal to the first derivative. I have not yet done the integral of the right-hand side. That's why I left it like that. It's a little bit easier to understand. Now, how do you integrate this? Substitution is not going to work out. You have this indestructible exponential function that's going to give you problems. But if you remember back to calculus 2 or 1, I can't remember, one of those, you'll remember integration by parts. And that's how you're going to have to do that. So the thing to look for integration by parts, for those of you who don't remember, is basically you need to have an indestructible function for it to work, which could be a sine or a cosine or whatever. And exponential is also indestructible. When I mean indestructible, I mean you take derivatives of it and it continues to come back in your face. It never gets any simpler. So it's indestructible. That's what I'm talking about. And then out in front of it, you have something that I'm going to call is destructible. If you keep taking derivatives of this guy, then it will eventually go away. So when you have a situation like that, same thing if it were t times the cosine, you would do integration by parts. If you have a destructible times indestructible, integration by parts is a great method to try at least. So that's what we're going to do. And so what we're going to do is we're going to start labeling these things. We're going to say u, in terms of integration by parts, is equal to t. And we're going to say dv is equal to e to the t dt. Because basically what you need to do, you need to rewrite this integral in terms of u and dv. So this is equal to u, then dv has to be equal to everything else left over. That's just how integration by parts works. So the next thing you do is you take the derivative of this guy, so du is equal to dt. And the next thing you do over here is you take the integral of this guy. So v is equal to integral of e to the t dt. And so obviously this is a really simple integral, e to the t. V is equal to e to the t because the integral of an exponential is itself an exponential. So you define u and dv, take the derivative of this guy, take the integral of this guy, and now you have u and du, and you have v and dv, and that's what you need in order to actually do integration by parts. Kind of going through this a little bit fast because this is really Calculus 1. You know, but everybody forgets stuff over time. I do. I know I do. I forget things all the time. So I'm trying to review as we go. Now, to do integration by parts, which is for this guy, we need to formulate u times v minus the integral of v du. We have everything we need to do that. That's why I always suggest you do all this mess first before you start writing the integration by parts down. U is equal to t, v is e to the t, minus the integral v is equal to e to the t, du is equal to dt. So once you have everything written, it's very easy to plug it into the integration by parts situation. So t e to the t minus that. So what do we have here? What do we have here to integrate this? Obviously, this is just sitting out in front. So we have t e to the t minus this integral is e to the t plus some constant 1. And so that is the answer to the integration by parts. So we've gotten that. So let's use that and rewrite our differential equation in terms of that. So dx dt is equal to t e to the t minus e to the t plus constant 1. This constant of integration arises from doing the integration in the first place. If you remember back when this was simpler, like in the last problem when it was a polynomial, we did the integration and we stuck a constant at the end. Well, that is what this constant is. It's the constant of integration from this integral. We just so happen to have to use integration by parts to get at the answer. All right. So next we're going to do is take the integral again, because we're going to try to solve for x. And so what we're going to do again is we're going to take the integral of this guy. So we take the integral of the left-hand side. We're going to get x as a function of time. And that's going to equal to the integral of t e to the t minus e to the t plus c1 dt. And I'll wrap it up in parentheses to make it look a little bit simpler. So the integral on the left-hand side gives us x, and then we still have to do the integral on the right. So x of t is equal to, now here's the deal. First term is t e to the t. We have to integrate that, but that's exactly what we already integrated. So here's where it gets a little bit complicated. You got to make sure and do your stuff right. So this guy, let me put a little bracket around it just to make sure we get, is exactly the same thing as what we calculated from up here. So we should get t e to the t minus e to the t. Okay, and then we still have to go ahead and let's put a constant of integration here, but for now, let me just keep it as a regular old c without a number. You'll see why I'm doing that here in just a second. So that is, this whole thing here is an integral, is the result of this integral, is a result of this little term right here, and it comes from what we did before. We just don't want to do it again if we've already done it once. Okay, now minus the integral of this term is very easy. It's just e to the t. And the integral of the last term is very easy. It's just c1 times t, right? And then we have a constant of integration from the end as well. So we'll call that c, right? Because we have, in general, we're integrating this guy, so we have a constant of integration that we always slap at the end. So what I'm going to do now is rewrite this. So x as a function of time is equal to, let's go ahead and simplify terms here. T e to the t, that's this term. These two terms can be combined, minus 2e to the t, because it's minus e to the t minus e to the t. Okay, this term is still here, plus c1 of t, that's from earlier. And we have a constant here and a constant here, so I'm just going to wrap both of those into another constant that I'm going to call c2. And that's what I wanted to point out to you. I'm basically taking this and I'm sort of adding it in with the other one, and so it makes one big giant constant at the end of the day that I'm calling C2. Because I know that at the end of the day, my general solution, which is what we have here, should have two constants, C1 and C2. It should have two constants because my differential equation is second order. You're always going to have the number of constants. The number of constants you have in your general solution is always going to be the same as the order of your differential equation, which is also going to be the same number of initial conditions you're going to need in order to plug in and calculate these things. So basically, when we did this stuff, we had to integrate this. At the end of the day, there's only one constant of integration that's really going to pop out of the end of that guy. I kind of kept one constant from here, and I kept another constant from here. But really, when you think about it, when you're integrating this thing here, you have C1t at the end of the day, we're really going to have one constant of integration left over, C2. And it just depends on how you prefer to look at it. I carry the constants around and then say, oh, I have two constants here. But they're all on the same level. It's going to make one big constant at the end. I'm going to call it C2. This is the general solution. Okay, the general solution, t e to the t minus 2e to the t plus c1t plus c2. Now, this is an infinite number of solutions dictated by these constants of integration. They all have a similar form starting off with this, but the tail end of it is going to differ depending on how things start out. In our case, our initial conditions are given. So let me write down the general solution again is x of t is equal to t e to the t minus 2e to the t plus c1t plus c2. And the initial conditions are x at time 0 is equal to the velocity at time 0 is equal to 0. So everything's basically not moving at the beginning, just like last time. So let's go ahead and use this one and plug it in there. All right, so at time 0, we have t e to the t, so we have 0 times e to the 0, right, because time is 0, minus 2e to the 0, because time is 0, plus c1 times 0, plus c2, and it's equal to 0. So I'm just plugging it in there. Now here's where things get a little different. Because we have exponentials, this one does drop out because we have 0 in front, but this guy, e to the 0, anything raised to the 0 power is 1. This guy does drop out, so what we end up having is minus 2 times the 1, so I'm going to leave it as minus 2 here, plus c2 from here is equal to 0. And so this means that constant number 2 is simply equal to 2. So here is a case where the constants are not always 0. And the other problems we've done, the constants always fell out where they were 0. It doesn't always have to be the case. Just even if you think they might, in this case it isn't. It's because this guy did drop to 0 because of this. This guy was 1. So this 2 hung around and we solved for C2. Now, next we need to have the first derivative and plug in for that. You could calculate the derivative here and then plug in. But if you look back, we already know what the derivative is. It's this. It's t e to the t. The first derivative is t e to the t minus this guy plus c1. So let me write that again just so we both, we're all familiar with it. The first derivative, just copying over t e to the t minus e to the t plus c1. That is what the first derivative is, so let's plug in for it. What we'll have is 0 times e to the 0 minus e to the 0, because time is 0, plus constant 1 is equal to 0. This guy goes away because of the 0 out front, but this guy does not go away. E to the 0 is 1. So what we have is minus 1 plus c1 is equal to 0, which means that constant 1 is equal to moving that guy over 1. So that's constant 1 is equal to 1. And so once we have that, we're basically done. We have constant 1 and constant 2. This is the general solution we just copied over from the other board. So x of t is equal to t e to the t minus 2e to the t plus. Constant 1 is 1. So I'm going to leave it, basically there's a c1 in front of here. I'm going to leave that 1 silent times t plus c2, which is given by 2. So this guy is the specific solution. T e to the t minus 2e to the t plus 2. That's a specific solution. So same sort of thing in this case. We have explored some examples of differential equations that were fairly easy. You had the derivatives on one side, you had the other junk, which is function of t, on the other side. You integrate as many times as you need using any tool that you know how to use in calculus. If these functions were sines and cosines and trigonometric in nature, then you would use your trigonometric identities from calculus 2 to figure it out. If they had logarithms and other crazy things, then you would use whatever tools you needed to take the integrals to get down to the point where you got x of t, which was down here, the general solution. The general solution is always going to have constants of integration rolling around there, because depending on what constants you put in here, you're going to get a different specific solution. So all of these general solutions represent an infinite number of solutions to this differential equation. In fact, if you want to take a little exercise, if you take this guy this general solution, and you put it into your differential equation, even with these constants, you will find that it works. It always works, no matter what the constant of C1 and C2 actually is. Because when you start taking those derivatives, what you're going to find is that they're going to disappear. So this general solution, there's an infinite number of ways in which you can satisfy that differential equation, no matter what numbers for C1 and C2 are actually in here. And that's sort of the moral of the story. Now, for the specific solution that we care about, these constants are going to be tied down based on what the initial conditions are, whether it's temperature, electric field, velocity, position, whatever it is, whatever your differential equation is describing. Which leads me to my conclusion. Differential equations are really everywhere. Every branch of engineering, every branch of physics, mathematics, chemistry even, they're everywhere because basically the world really does obey rate of change, how fast something is changing. I mean, the force on an object really does depend on the rate of change of the position. That's F equals ma. We talked about that. There are lots of different things when you get into heat transfer, fluid flow, turbulent flow, electric fields, waves, anything like that, where there really are differential equations. Now, when you're in Physics 1, they sanitize it a little bit for you and hide the differential equations off somewhere else so that you're not really staring at them, because you don't want to get too bogged down in that part of it. You're trying to understand the physics, but they're there. And so now that you have these tools available to you, you're going to find you can solve lots of different, much more complicated problems. And that's sort of the whole point, isn't it? So I'm Jason. I hope that you've learned something from this. This is sort of an introductory section, giving you a good idea of what is a differential equation, what is a solution, what do they mean when they talk about a general solution. In the subsequent sections, we're going to tackle specific classes of differential equations. We're going to start off with the first order equations. We're going to go into the second order and on after that. We're going to learn a lot of different techniques. So we're going to practice them all. You need to be good at them all, and you'll do just fine in your homework and on your exams.